The Fury of the Sun, a documentary by Night Tales. The star we call home. It is the heart of our solar system, a nuclear furnace that holds 99.86% of all the mass in our cosmic neighborhood. We call it the Sun. For billions of years, it has been the silent, steady source of life, the warmth that thaws the ice, the light that paints our skies blue, the energy that drives the engine of evolution itself. Every morning, without fail, it rises in the east. Every evening, it sets in the west. We have built our civilizations around this rhythm. Our calendars, our festivals, our very concept of time all revolve around this great golden disk in the sky. We take it for granted. It rises, it sets. It is the clock by which we measure our lives. But beneath its serene golden surface lies a beast of incomprehensible power. A beast that has been burning for 4.5 billion years. A beast that consumes itself every single second, turning mass into energy with an efficiency that no human technology could ever hope to match. This is not just our friend. This is a volatile, unpredictable star. In its heart, hydrogen atoms are crushed together with such force that they fuse into helium. This is nuclear fusion, and it happens with the force of millions of atomic bombs going off every single second. It is a fury so immense, so violent, that if the scale of this reaction were altered by just a fraction of a percent, life on Earth would cease to exist entirely. Think about that for a moment. We live on a planet that orbits a star. That star is a bomb. A bomb so large that it could swallow 1 million Earths. A bomb that has been exploding continuously for billions of years. And we are sitting right next to it. The only thing protecting us is a distance of 93 million miles and a fragile magnetic bubble that we call the magnetosphere. For centuries, we worshipped the sun. We called it Ra in ancient Egypt. The Egyptians believed that Ra sailed across the sky in a solar boat, bringing light and life to the world. The Greeks called it Helios, a god who drove a chariot of fire across the heavens. In India, it was Surya, the all-seeing eye of the universe. In Japan, it was Amaterasu, the great goddess of the sun. We saw the warmth, we felt the life-giving energy, but we also feared the burning eye in the sky. We knew, deep in our ancient bones, that this was a force beyond our control. Today, in our modern age of technology and science, we have grown complacent. We have forgotten that our planet is merely a speck of dust in the path of a cosmic hurricane. We have built satellites, power grids, undersea cables, and wireless networks. We have connected the entire world with invisible threads of data, and all of it, every single part of it, is vulnerable to the temperament of a single star. Part 1 of this series explores the duality of our star, the giver of life and the destroyer of worlds. It explores the science, the history, and the terrifying reality of solar storms. It explores what happens when the sun wakes up from its slumber and reminds us who is really in charge. We are not safe. We are merely in the calm before the storm. This is the story of the sun's hidden fury and the ticking clock that hangs above our heads. A clock that is counting down to the next great solar event. An event that could change human civilization forever. The engine of chaos. To understand the fury, we must first understand the machine. We must travel deep into the heart of the sun, to a place that no human probe has ever reached. A place of unimaginable pressure and temperature. A place where the very laws of physics are pushed to their limits. Deep within the core, 500,000 kilometers beneath the visible surface, the temperature reaches 15 million degrees Celsius. That is 15 million degrees. To put that in perspective, The surface of the Sun is only about 5,500 degrees. The core is nearly 3,000 times hotter than the surface. The pressure at the core is so crushing that it is equivalent to 250 billion times the atmospheric pressure we feel here on Earth. Under these extreme conditions, the very atoms of hydrogen are stripped apart. Their electrons are torn away, leaving only naked protons. These protons are packed so tightly together that they overcome their natural electrical repulsion and fuse together. This is nuclear fusion. This is the engine that powers the Sun. Every second, this cosmic engine converts 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons? That is pure energy. Mass converted into energy according to Einstein's famous equation, E equals mc squared. And that energy is released as light and heat. But this energy does not escape easily. It is trapped. It is trapped inside a dense, opaque plasma that is so thick that photons of light can barely move through it. The photons generated in the core bounce around inside this plasma for thousands of years, sometimes hundreds of thousands of years. They travel in a random zigzag path, colliding with particles, being absorbed and re-emitted, slowly making their way toward the surface. This is called the radiative zone. It is a region of the Sun where energy is transported by radiation. It extends from the core to about 70% of the Sun's radius. Here, the temperature drops from 15 million degrees down to about 2 million degrees. The density also decreases, but it is still so dense that light takes an incredibly long time to pass through. Beyond the radiative zone lies the convective zone. This is where things get really interesting. The convective zone extends from about 70% of the Sun's radius all the way to the surface. Here, the temperature is low enough that the plasma becomes opaque. It absorbs the radiation and heats up. The hot plasma rises to the surface, cools down, and sinks back down. This is convection. It is the same process that happens when you boil water in a pot. Look at the surface of the Sun through a telescope. Those bubbling cells that you see, they are called granules. Each one is the size of Texas. They are the visible evidence of convection. Hot plasma rising from below, releasing its heat and sinking back down. This constant churning creates a magnetic field. The Sun is a giant magnet. It has a north pole and a south pole. But unlike Earth, the Sun's magnetic field is not stable. It is constantly twisting and tangling. The plasma moving inside the Sun acts like a dynamo. It generates electrical currents. These currents generate magnetic fields. And these magnetic fields are the key to the Sun's fury. The magnetic field of the Sun is the engine of chaos. It is the force that drives everything. The sunspots, the solar flares, the coronal mass ejections. Every violent event on the Sun is driven by the magnetic field. It twists, it tangles, it snaps. And when it snaps, it releases an enormous amount of energy. Energy that travels across the solar system and affects everything in its path. We have satellites monitoring this magnetic field 24 hours a day, 7 days a week. We have the Solar Dynamics Observatory, or SDO, watching the Sun in multiple wavelengths of light. We have the Solar and Heliospheric Observatory, or SOHO, peering deep into the Sun's atmosphere. We have the Parker Solar Probe, flying closer to the Sun than any spacecraft in history. We are watching the Sun constantly because when the magnetic field snaps, we feel it here on Earth. And when it snaps, it creates sunspots. Sunspots are the visible evidence of this magnetic chaos. They are cooler areas on the surface, regions where the magnetic field is so strong that it suppresses the rising hot plasma. They appear dark against the brighter surrounding surface, but appearances can be deceiving. Sunspots are not just dark patches. They are the gates to the apocalypse. They are the locations where the sun's magnetic field is most tangled. And it is around these sunspots that the sun unleashes its deadliest weapons. The weapons of the sun. In 1859, a British astronomer named Richard Carrington was observing the sun through his telescope. He was sketching sunspots, as astronomers often did in those days. Suddenly, he saw something extraordinary. A brilliant flash of white light erupted from the surface of the sun. It was so bright that it illuminated the entire solar disk. It lasted for only a few minutes, but Carrington knew he had witnessed something historic. It was the first recorded solar flare. Little did Carrington know that he had just witnessed a flare that would nearly electrocute the entire planet. Hours later, the skies over the Caribbean turned blood red. People thought the world was ending. The northern lights, the aurora borealis, were visible as far south as Hawaii and Cuba. They were so bright that people could read newspapers at midnight. But more terrifyingly, telegraph systems across Europe and North America went haywire. Sparks flew from the machines. Telegraph operators received electric shocks. Paper caught fire. The telegraph system, the cutting-edge technology of the 19th century, had been crippled by the sun. This was the Carrington Event, the first time humanity truly realized that the sun has a temper. We had always known that the sun was powerful, but we had never imagined that it could reach across 93 million miles and affect our technology. Today, we know that the Carrington Event was caused by a massive coronal mass ejection, a cloud of electrified gas that took only 17 hours to travel from the sun to the Earth. The sun has two primary weapons, two ways that it can attack our planet, two ways that it can remind us of our fragility. The first weapon is the solar flare. A solar flare is a sudden explosion of electromagnetic radiation, X-rays, gamma rays, extreme ultraviolet light. It is caused by the sudden release of magnetic energy stored in the sun's atmosphere. When the magnetic field lines reconnect, they release an enormous burst of energy. This energy accelerates particles to near-light speeds and emits radiation across the entire electromagnetic spectrum. This radiation travels at the speed of light. It takes only 8 minutes to reach Earth. 8 minutes. That means that by the time we see a solar flare, it has already hit us. There is no warning. There is no time to prepare. The radiation is already here. If a massive X-class flare, the most powerful category of solar flare, hits Earth, it instantly disrupts high-frequency radio communications on the side of the Earth facing the sun. It can knock out GPS satellites by disrupting their signals. It can scramble the data that guides our airplanes and ships. It can disrupt military communications. It can cause radio blackouts that last for hours. But the solar flare is just the opening salvo. The second weapon is the true beast. It is the coronal mass ejection, or CME. A CME is a massive bubble of plasma and magnetic field that is ejected from the sun's corona. It is 1 billion tons of electrified gas hurled into space at speeds of up to 7 million kilometers per hour. 7 million kilometers per hour. That is almost 2,000 kilometers per second. At that speed, a CME can travel from the sun to the Earth in less than a day. Imagine 1 billion tons of plasma, a magnetic pulse 1 billion times more powerful than a nuclear blast, tearing through the vacuum of space, expanding as it travels, carrying with it the twisted magnetic fields of the sun. This is a CME. This is the weapon that can cripple our civilization. When a CME hits Earth, it crashes into our magnetic shield, the magnetosphere. The magnetosphere is the bubble of magnetic field that surrounds our planet. It is created by the movement of molten iron in Earth's core. It is our first line of defense against the solar wind and cosmic radiation. But it is not invincible. The CME compresses the magnetosphere on the day side of Earth and stretches it on the night side. This compression allows solar particles to penetrate our atmosphere. The particles follow the Earth's magnetic field lines down toward the poles. They collide with atoms and molecules in the atmosphere, and the result is the aurora borealis and aurora australis, the northern and southern lights. The auroras are beautiful. They are one of the most spectacular natural phenomena on Earth. They dance across the sky in shimmering curtains of green, red, purple, and blue. But they are not just a light show. They are the visible sign of an invisible war being waged above our heads. They are the evidence of the Earth's magnetic field fighting off the solar assault. The particles moving down the magnetic field lines superheat the upper atmosphere. They add energy to the thermosphere, the layer of the atmosphere where the International Space Station and most satellites orbit. This heating causes the atmosphere to expand. This expansion is a problem. As the atmosphere expands, it creates drag on satellites. The same way that air resistance slows down a car, atmospheric drag slows down satellites. This drag pulls satellites from their orbits. It lowers their altitude. It increases their fuel consumption as they try to maintain their position. If the drag is strong enough, it can de-orbit satellites entirely. In February of 2022, a minor geomagnetic storm knocked 38 Starlink satellites out of orbit. They were newly launched, and they were still in low orbit. The storm caused the atmosphere to expand, and the satellites were unable to fight the drag. They re-entered the atmosphere and burned up. A minor storm. A minor storm destroyed 38 satellites. Now imagine a major storm. Imagine a Carrington-level event. Imagine a storm so powerful that it superheats the atmosphere for days or even weeks. Imagine the drag on every satellite in orbit. The GPS satellites, the communication satellites, the weather satellites, the military satellites, all of them experiencing drag, all of them struggling to stay in orbit, all of them potentially falling out of the sky. The target, Earth. Our modern world is a house of cards. It is built on a foundation of electricity and data. Every aspect of our lives depends on the smooth flow of electrons through wires and the smooth transmission of data through the air and through cables. We have built a civilization that is incredibly efficient, but it is also incredibly fragile. A Carrington-level event today would not just burn a few telegraph wires. It would cripple the infrastructure of the 21st century. It would expose the vulnerability of our interconnected world. The coronal mass ejection distorts the Earth's magnetic field. It changes the magnetic field that surrounds our planet. And when a magnetic field changes, it induces an electric current in any conductor. This is Faraday's law of induction. It is the principle that powers generators and transformers. It is also the principle that can destroy our power grids. Our power grids are the largest conductors on Earth. They are vast networks of copper and aluminium wires that stretch across continents. They carry electricity from power plants to our homes, our factories, our hospitals, and our offices. They are the circulatory system of our civilization. When a CME hits Earth, it induces currents in these power lines. These are called geomagnetically induced currents, or GICs. These currents flow through the power lines and into the transformers. Transformers are the devices that step up and step down voltage. They are essential for the transmission of electricity. They are also extremely vulnerable to GICs. GICs overload transformers. They saturate the magnetic cores of the transformers, causing them to heat up. The heat is intense. It melts the insulation. It melts the copper windings. It destroys the transformer. A single damaged transformer can take down a large portion of the grid. Thousands of damaged transformers could take down the entire grid. And here is the real problem. Transformers are not off-the-shelf parts. They are custom built. They can take up to a year or more to manufacture. If thousands of transformers are destroyed, it would take years to replace them. Years without power. Years without electricity. Imagine the world in a blackout. Not for hours, but for months, perhaps years. No water purification, because the pumps rely on electricity. No refrigeration for food or medicine. No internet. No banking. Our digital economy would vanish in a flash. The internet, the backbone of our civilization, is largely connected by undersea fiber optic cables. These cables carry data across the ocean floor. They connect continents. They are the arteries of our global communication system. While the cables themselves use light to transmit data, which does not carry electric current, the repeaters and amplifiers along the cables that boost the signal are powered by copper wires. These copper wires are vulnerable to induced currents. A powerful CME could damage these repeaters. It could knock out the internet, not just in one country, but across the entire globe. No internet, no email, no streaming, no social media, no online banking, no e-commerce. The digital economy would collapse. Our aircraft would lose GPS navigation. Modern aircraft rely on GPS for precision navigation. Without GPS, pilots would have to rely on traditional navigation methods, which are less precise. This could lead to delays, diversions, and even accidents. Air traffic control systems would be strained. The global aviation industry would be grounded. Hospitals would struggle. They have backup generators, but those generators need fuel. Fuel that is delivered by trucks. Trucks that run on diesel. Diesel that is refined in oil refineries. Oil refineries that need electricity. In a prolonged blackout, the fuel supply would run out. Hospitals would be forced to prioritize. Who gets life-saving treatment? Who is left to die? Global supply chains would freeze. The world economy is based on just-in-time delivery. Goods are produced in one country and shipped to another. They are stored in warehouses and moved by trucks, trains, and ships. All of these systems depend on electricity. Without electricity, the supply chains would stop. Food would rot in warehouses. Medicines would expire. Essential supplies would not reach those who need them. The recovery from a superflare would be measured not in dollars, but in decades. The economic cost would be measured in trillions of dollars. The human cost would be measured in lives lost. The social cost would be measured in the breakdown of order and the rise of chaos. But we are not entirely defenseless. We have warning systems. NASA and the National Oceanic and Atmospheric Administration, NOAA, have a fleet of spacecraft watching the sun constantly. These spacecraft are our solar sentinels. The Solar and Heliospheric Observatory, SOHO, watches the sun from a special point in space called the L1 Lagrange point. This point is about 1.5 million kilometers from Earth, directly between the Earth and the sun. From this vantage point, SOHO can see the sun 24 hours a day. It can detect solar flares. It can detect coronal mass ejections. The Solar Dynamics Observatory, SDO, is another solar sentinel. It orbits Earth and monitors the sun in multiple wavelengths of light. It sees things that the human eye cannot see. It sees the magnetic field lines. It sees the plasma boiling on the surface. It sees the buildup of energy before a flare or a CME. These satellites give us warning. They give us perhaps a few hours' notice at best before a CME reaches Earth. A few hours to take action. A few hours to shut down vulnerable systems. A few hours to prepare for the storm. A few hours. That is all the time we have. The looming threat. So, what is the prognosis? Are we doomed? Is humanity destined to be knocked back to the Stone Age by a cosmic tantrum? The good news is that we are no longer in the dark, literally and figuratively. We understand the sun better than ever before. We have satellites watching it constantly. We have scientists studying it continuously. We are building models to predict its behavior. We are building early warning systems to alert us to impending danger. We are also taking steps to protect our infrastructure. We are hardening our power grids. We are installing devices that can block geomagnetically induced currents. We are building surge protectors for our transformers. We are developing strategies for rapid recovery. We are studying the sun's 11-year cycle of activity so we can anticipate when the risks are highest. But the bad news is that we are behind the curve. The sun is currently entering a period of maximum activity, a phase in its 11-year cycle where the number of sunspots and flares increases. This phase is called solar maximum. During solar maximum, the sun is more active. It produces more sunspots. It produces more flares. It produces more CMEs. And it is during solar maximum that the risk of a major geomagnetic storm is greatest. We are behind the curve. Our infrastructure is old. Much of our power grid was built in the mid-20th century. It was not designed to withstand a solar storm. It was not designed with resilience in mind. It was designed for efficiency, not robustness. We are trying to upgrade it, but the process is slow. It is expensive, and it is not keeping pace with the growing threat. A major solar storm is not a matter of if, it is a matter of when. The sun has been active for 4.5 billion years. It will continue to be active for another 5 billion years. It will produce flares. It will produce CMEs. It is only a matter of time before one of these events is aimed directly at Earth. When that happens, we will face a crisis like no other in human history. It will not be a war. It will not be a pandemic. It will not be a climate disaster. It will be something that touches every person on the planet simultaneously. A global crisis that tests the very limits of our civilization. We owe our existence to the sun. It is the source of all life on Earth. The plants that feed us depend on sunlight. The oxygen we breathe is produced by photosynthesis, a process powered by the sun. The fossil fuels we burn are the stored energy of ancient sunlight. The sun is the ultimate source of almost all the energy we use. But the sun is a harsh master. It gives life, but it can also take it away. It is the source of our warmth, but it can also burn us. It is the source of our light, but it can also blind us. It reminds us that we live on a fragile planet, a planet that spins in the cosmic crosshairs of a celestial titan. The fury of the sun is the greatest natural disaster we have yet to truly face. We have conquered plagues. We have survived ice ages. We have mastered the atom. We have walked on the moon. We have sent probes to the outer reaches of the solar system. But the fire in the sky? We are only just beginning to understand it, and we are running out of time. The sun is waking up. It is becoming more active. The next solar maximum is approaching, and with it comes the greatest threat we have ever known. Not an asteroid, not a supervolcano, not a nuclear war, but a solar storm. A storm that could silence the world. A storm that could plunge us into darkness. We have a choice. We can continue to ignore the threat. We can hope that the sun will spare us. We can hope that the next big storm will miss Earth. Or we can prepare. We can invest in resilience. We can harden our infrastructure. We can build the systems that will protect us. We can develop the strategies that will help us recover. The choice is ours, but time is running out. The sun does not wait. It does not negotiate. It does not care about our technology, our economy, or our civilization. It is a star, a vast, powerful, unpredictable star, and it is awakening. In part 2 of this series, we will explore the science of prediction. We will look at the secret missions to send probes directly into the sun's atmosphere to touch the fire. We will explore the cutting-edge research that is helping us understand the sun like never before. We will look at the technologies that could protect us from the fury of the sun. We are not helpless. We are not doomed, but we must act. We must prepare. We must respect the power of our star, because the fury of the sun is coming. It is only a matter of time. The final warning. Let us consider what a modern Carrington event would look like. It would begin with a brilliant flash of light on the sun, a solar flare. The flare would be detected by our satellites. Scientists around the world would be alerted. The news would spread rapidly, but it would already be too late. The radiation from the flare would reach Earth in 8 minutes. It would disrupt radio communications. It would scramble GPS signals. It would interfere with military radar. The first signs of the storm would be chaotic, confusion, uncertainty, and then the CME would arrive. 17 hours after the flare. 17 hours to prepare. 17 hours to shut down the power grid. 17 hours to protect the transformers. 17 hours to disconnect the internet. 17 hours to warn the public. In 17 hours, we could save some of our infrastructure. We could shut down critical systems. We could protect the most important transformers. We could save some lives. But we could not save everything. We could not save everyone. There would be damage. There would be loss. There would be chaos. The power grid would fail. Transformers would melt. The lights would go out. The internet would go down. Communications would be disrupted. The global economy would grind to a halt. Food would rot. Medicines would spoil. Hospitals would struggle. The recovery would take years, decades, perhaps a generation. We would rebuild. We would learn. We would make our infrastructure more resilient. We would prepare for the next storm. But we would never forget the day the sun attacked us. The day the sky turned red. The day the lights went out. The day we remembered that we are not the masters of the universe. We are just passengers on a tiny planet, dancing around a fiery star. And there will be a next storm. The sun does not stop. It does not rest. It continues its 11-year cycle of activity. It continues to produce flares and CMEs. It continues to be the unpredictable, volatile star that it has always been. And one day, another CME will be aimed directly at Earth. We must learn to live with the fury of the sun. We must respect its power. We must prepare for its temper. We must remember that we are not invincible. We are not invulnerable. We are just human, and the sun is a star. So let us look up at the sky. Let us appreciate the warmth. Let us appreciate the light. Let us appreciate the life-giving energy, but let us never forget the danger. Let us never forget that the sun is a beast that gives and takes, a beast that creates and destroys, a beast that we must learn to fear, respect, and ultimately to survive. The fury of the sun is the greatest challenge we have ever faced, and it is a challenge that we must meet head-on, with science, with preparation, with resilience, with the determination to survive. Because the sun is not going away, and neither are we. Looking ahead. As we conclude part 1 of this documentary, We have journeyed deep into the heart of our star. We have explored its inner workings. We have witnessed its terrible weapons. We have seen the vulnerability of our modern civilization. We have felt the ticking of the cosmic clock. But this is only the beginning. In part 2, we will go further. We will look at the future of solar science. We will explore the bold missions that are sending spacecraft into the sun's atmosphere. We will meet the scientists who are risking everything to understand our star. We will see the cutting-edge technologies that could protect us from the fury of the sun. We will look at the Parker Solar Probe, a spacecraft that is diving directly into the sun's corona. It is a mission of incredible bravery and engineering brilliance. It is traveling closer to the sun than any spacecraft in history. It is enduring temperatures of over 1,000 degrees Celsius. It is giving us data that is revolutionizing our understanding of the sun. We will look at the Solar Orbiter, a joint mission of NASA and the European Space Agency. It is studying the sun's poles for the first time. It is giving us a new perspective on our star. It is helping us understand the sun's magnetic field and how it drives solar activity. We will look at the future of space weather prediction. We will explore the technologies that could give us days, not hours, of warning before a CME hits Earth. We will explore the possibility of creating artificial magnetic shields to protect our planet. We will look at the future of our civilization in the shadow of the sun. We will also look at the human story, the story of the scientists who dedicate their lives to studying the sun, the story of the engineers who build the spacecraft and the satellites, the story of the policymakers who must decide how to protect our infrastructure, the story of all of us living in a world that is increasingly vulnerable to the fury of the sun. So join us on this journey. Join us as we explore the fury of the sun. Join us as we learn to live with our star. Join us as we face the greatest challenge in human history. The sun is waking up, and we must be ready. Watching the fire, the science of survival. The new frontier. In part 1 of this series, we explored the heart of our star. We witnessed its nuclear fury. We saw its terrifying weapons. We understood the vulnerability of our modern world. We learned that the sun is not just our friend. It is a volatile, unpredictable beast. A beast that gives life, but a beast that can also take it away. We ended with a warning. The sun is waking up. It is entering a period of maximum activity. The next great solar storm is not a matter of if, it is a matter of when. And when it comes, it will test the very limits of our civilization. But we are not helpless. We are not doomed. We are not simply waiting for the apocalypse. We are fighting back. We are exploring. We are innovating. We are building the technologies that will protect us. We are sending spacecraft into the very heart of the fire. Into the very heart. This is part 2 of our journey. This is the story of our quest to understand the sun. This is the story of the brave men and women who are risking everything to touch the fire. This is the story of the science that could save our civilization. The sun is the closest star to Earth. It is the only star we can study up close. It is our laboratory. It is our teacher. It is our greatest challenge. And we are finally ready to meet that challenge. In the last 2 decades, we have launched a fleet of spacecraft dedicated to studying the sun. We have placed satellites in orbit around Earth. We have placed satellites at the L1 Lagrange point, a special point in space where the gravity of the Earth and the sun balance out. We have even sent a spacecraft into the sun's atmosphere. We are studying the sun in ways that our ancestors could never have imagined. We are using telescopes that can see in multiple wavelengths of light. We are using instruments that can measure magnetic fields. We are using detectors that can count particles. We are using computers that can simulate the sun's behavior. We are building a comprehensive picture of our star, a picture that is helping us predict its behavior, a picture that is helping us prepare for its fury. But the sun is not easy to study. It is incredibly hot. It is incredibly bright. It is incredibly dangerous. Spacecraft that get too close to the sun are destroyed. Instruments that point directly at the sun are blinded. Scientists who study the sun must be careful. They must be precise. They must be brave. The quest to understand the sun is one of the greatest scientific adventures of our time. It is a quest that has already yielded incredible discoveries. It is a quest that is changing the way we think about our place in the universe. It is a quest that could save our civilization. Part 2 of this documentary, we will explore this quest. We will look at the missions that are pushing the boundaries of science and engineering. We will look at the discoveries that are revolutionizing our understanding of the sun. We will look at the future of space weather prediction, and we will look at the technologies that could protect us from the fury of the sun. So join us as we journey to the sun. Join us as we touch the fire. Join us as we learn to live with our star, the solar sentinels. Before we can understand how to protect ourselves from the sun, we must first understand the sun itself. We must watch it. We must monitor it. We must study it. We must build a network of observatories that can see the sun from every angle. We must build a fleet of spacecraft that can measure the sun's every move. This fleet is called the Solar Sentinels. It is a network of satellites and ground-based observatories that watch the sun 24 hours a day, 7 days a week. It is our early warning system. It is our eyes and ears in the solar system. The most important of these solar sentinels is the Solar and Heliospheric Observatory, or SOHO. SOHO was launched in 1995. It was a joint mission of NASA and the European Space Agency. It was placed at the L1 Lagrange point, about 1.5 million kilometers from Earth, directly between the Earth and the Sun. From this vantage point, SOHO has a clear view of the sun at all times. It never has the Earth blocking its view. It never has the moon blocking its view. It can see the sun continuously. And it has been seeing the sun continuously for nearly 30 years. SOHO carries 12 instruments. These instruments measure the sun's interior, its surface, its atmosphere, and its magnetic field. They observe the sun in multiple wavelengths of light. They detect solar flares. They detect coronal mass ejections. They monitor the solar wind. They have given us an unprecedented view of our star. SOHO has discovered thousands of comets. It has watched the sun go through 2 full 11-year solar cycles. It has witnessed the most powerful solar flares ever recorded. It has been the backbone of our solar monitoring system for decades. It is still operating today. It is still sending back data. It is still watching the sun. But SOHO is not alone. It is part of a larger fleet. There is the Solar Dynamics Observatory, or SDO. SDO was launched in 2010. It is a NASA mission that orbits Earth. It observes the sun in high resolution. It takes images of the sun every 12 seconds. It captures details that are smaller than the size of the United States. It sees the sun in ways that we have never seen it before. SDO studies the sun's magnetic field. It studies the sun's atmosphere. It studies the sun's interior. It helps us understand how the sun works. It helps us predict solar storms. It is a vital part of our early warning system. There is also the Solar Terrestrial Relations Observatory, or STEREO. STEREO was launched in 2006. It is a pair of spacecraft. One spacecraft orbits ahead of Earth. The other orbits behind Earth. Together, they give us a 3-dimensional view of the sun. They allow us to see the sun from multiple angles. They allow us to track coronal mass ejections as they travel toward Earth. They allow us to see the sun's far side. Before stereo, we could only see the side of the sun facing Earth. If a solar flare erupted on the far side of the sun, we would not know about it. We would be caught off guard. But with stereo, we can see the entire sun. We can see flares and CMEs from every angle. We can track them as they travel through the solar system. We can predict when they will reach Earth. There is also the Advanced Composition Explorer, or ACE. A CE was launched in 1997. It is positioned at the L1 Lagrange point, just like SOHO. But ACE does not observe the sun directly. Instead, it measures the solar wind. It measures the particles that stream from the sun. It measures the magnetic field that is carried by the solar wind. It tells us what is coming. A CE is our first line of defense. It is the first spacecraft to detect a CME. It is the first to measure its speed. It is the first to measure its magnetic field. It gives us about an hour of warning before a CME reaches Earth. That is not much time, but it is enough to shut down critical systems. It is enough to protect some of our infrastructure. It is enough to save lives. Together, these spacecraft form the Solar Sentinels. They are our eyes and ears in the solar system. They are our early warning system. They are our protectors. They are the first step in our defense against the fury of the sun. Touching the sun. Watching the sun from a distance is important, but it is not enough. To truly understand the sun, we must get closer. We must send spacecraft into the sun's atmosphere. We must touch the fire. This is the most ambitious goal in solar science. It is a goal that has driven scientists and engineers for decades. It is a goal that requires incredible bravery, ingenuity, and precision. It is a goal that is finally being achieved. The Parker Solar Probe is the most remarkable spacecraft ever built. It is a NASA mission that was launched in 2018. It is designed to fly directly into the sun's corona, the outermost layer of the sun's atmosphere. It will travel closer to the sun than any spacecraft in history. It will get within 6 million kilometers of the surface. That is 7 times closer than any spacecraft has ever been. At this distance, the temperatures are extreme. The heat is intense. The radiation is deadly. The Parker Solar Probe must survive temperatures of over 1,400 degrees Celsius on its sun-facing side. That is hot enough to melt steel. That is hot enough to melt glass. That is hot enough to melt almost anything. To survive, the Parker Solar Probe is equipped with a revolutionary heat shield. The heat shield is made of carbon composite. It is 4.5 inches thick. It is covered with a white ceramic coating that reflects sunlight. The heat shield faces the sun at all times. It protects the spacecraft's instruments from the intense heat. It keeps them at room temperature, even as the heat shield blazes at over 1,400 degrees. The Parker Solar Probe carries 4 instrument suites. These instruments measure the solar wind, the magnetic field, the plasma, and the energetic particles. They take pictures of the sun's corona. They measure the temperature and density of the plasma. They measure the speed and direction of the solar wind. They measure the electric and magnetic fields. The data from the Parker Solar Probe is revolutionizing our understanding of the sun. It is helping us answer fundamental questions. Why is the sun's corona so hot? The corona is millions of degrees, while the surface is only thousands of degrees. This is a paradox. It is like walking away from a fire and getting hotter. The Parker Solar Probe is helping us understand why. The Parker Solar Probe is also helping us understand the solar wind. The solar wind is a stream of charged particles that flows from the sun. It travels at supersonic speeds. It fills the entire solar system. It interacts with the Earth's magnetosphere. It causes auroras. It causes geomagnetic storms. The Parker Solar Probe is helping us understand where the solar wind comes from and how it is accelerated. And the Parker Solar Probe is helping us understand coronal mass ejections. It is flying through the region where CMEs are born. It is measuring the magnetic fields that drive them. It is measuring the plasma that forms them. It is giving us the data we need to predict when they will occur and how strong they will be. The Parker Solar Probe is not alone in this quest. There is also the Solar Orbiter. The Solar Orbiter is a joint mission of NASA and the European Space Agency. It was launched in 2020. It is designed to study the Sun from a unique perspective. It will orbit the Sun at an angle that allows it to see the Sun's poles. The Sun's poles are a mystery. We have never studied them closely. We do not know what they look like. We do not know how they behave. We do not know how they influence the Sun's magnetic field. The Solar Orbiter will change that. It will give us the first close-up images of the Sun's poles. It will help us understand the Sun's magnetic field in a way that we never have before. The Solar Orbiter carries 10 instruments. These instruments measure the Sun's magnetic field, the solar wind, the plasma, and the energetic particles. They take images of the Sun's surface and atmosphere. They study the Sun's magnetic field lines. They help us understand the Sun's 11-year cycle. They help us predict the Sun's behavior. Together, the Parker Solar Probe and the Solar Orbiter are revolutionizing our understanding of the Sun. They are giving us the data we need to predict solar storms. They are giving us the data we need to protect our civilization. They are touching the fire. But these missions are not without risk. The Parker Solar Probe must survive the most extreme environment in the solar system. It must endure temperatures that would melt most materials. It must endure radiation that would destroy most electronics. It must endure the intense gravity of the Sun. It must navigate with precision, using Venus and Mercury to adjust its orbit. It must fly through the corona, a region of the Sun's atmosphere that has never been explored. The engineers who built the Parker Solar Probe are heroes. They have pushed the boundaries of engineering. They have built a spacecraft that can survive conditions that are beyond anything we have ever attempted. They have made the impossible possible. The scientists who work with the Parker Solar Probe are heroes. They are analyzing data that is changing our understanding of the Sun. They are making discoveries that will help us predict solar storms. They are pushing the boundaries of knowledge. They are touching the fire. The science of prediction. Understanding the Sun is one thing. Predicting its behavior is another. The Sun is a chaotic, complex system. Its behavior is influenced by countless factors. Its magnetic field is constantly twisting and tangling. Its plasma is constantly moving and flowing. Its surface is constantly bubbling and erupting. Predicting the Sun is like predicting the weather, but it is much harder. The weather on Earth is influenced by the Sun, the oceans, the atmosphere, and the land. It is a complex system, but we can observe it, we can measure it, we can model it, we can predict it with reasonable accuracy. The Sun is different. It is 100 times larger than the Earth. It is 1,000,000 times more massive. It is 1,000,000,000 times more energetic. It is made of plasma, not gas. Its magnetic field is 1,000 times stronger than Earth's. Its behavior is driven by forces that we do not fully understand. Predicting the Sun is one of the greatest challenges in modern science, but we are making progress. We are building models that simulate the Sun's behavior. We are using supercomputers to run these models. We are using data from our satellites to validate these models. We are getting better at predicting solar storms. There are 3 levels of space weather prediction. The first level is long-term prediction. This is predicting the Sun's 11-year cycle. We know that the Sun goes through periods of high and low activity. We know that during solar maximum, the Sun produces more sunspots, more flares, and more CMEs. We know that during solar minimum, the Sun is quieter. Long-term prediction is relatively easy. We have been observing the sun's cycle for centuries. We know its rhythms. We know its patterns. We can predict when solar maximum will occur and when solar minimum will occur. But we cannot predict exactly how strong solar maximum will be. We cannot predict exactly how many sunspots there will be. We cannot predict exactly how many flares there will be. Long-term prediction is accurate, but it is not precise. The second level is short-term prediction. This is predicting solar flares and CMEs days or hours before they occur. This is much harder. Solar flares are sudden. They are caused by the sudden release of magnetic energy. They can occur without warning. They can happen anywhere on the sun's surface. They can be triggered by a change in the magnetic field that we cannot see. But we are getting better at short-term prediction. We are using machine learning and artificial intelligence to analyze the sun's magnetic field. We are looking for patterns that precede solar flares. We are looking for signs that a flare is about to occur. We are developing algorithms that can predict flares with increasing accuracy. The third level is real-time prediction. This is predicting the impact of a CME once it has been detected. This is the most important level. This is the level that gives us the warning we need to protect our infrastructure. When a CME is detected by our satellites, we must predict its speed. We must predict its direction. We must predict its magnetic field. We must predict when it will reach Earth. We must predict how strong its impact will be. This requires complex models of the solar wind and the Earth's magnetosphere. We have models that can predict the trajectory of a CME. We have models that can predict its speed. We have models that can predict its magnetic field. We have models that can predict its impact on the Earth's magnetosphere. These models are getting better. They are more accurate. They are more reliable. They are giving us more warning. But there is a problem. The models are not perfect. They require data, and the data is not always available. Our satellites can see the sun. They can detect CMEs, but they cannot see inside a CME. They cannot measure its magnetic field directly. They can only measure it indirectly. This introduces uncertainty. This means that our predictions are not always accurate. We are working to improve our predictions. We are building new satellites. We are developing new instruments. We are using new technologies. We are making progress. But we still have a long way to go. The future of space weather prediction is exciting. We are developing new models that will give us more accurate predictions. We are developing new algorithms that will give us more warning. We are developing new satellites that will give us better data. We are moving towards a future where we can predict solar storms with the same accuracy that we predict the weather. That future cannot come soon enough. The sun is waking up. Solar maximum is approaching. And when it comes, we need to be ready. Protecting the grid. Predicting solar storms is essential, but it is not enough. We must also protect our infrastructure. We must harden our power grids. We must protect our transformers. We must build resilience. We must prepare for the worst. Our power grids are the circulatory system of our civilization. They carry electricity from power plants to our homes, our businesses, our hospitals, and our schools. They are essential for modern life. They are also vulnerable to solar storms. The threat comes from geomagnetically induced currents, or GICs. These are currents that are induced in the power lines by the changing magnetic field of a CME. These currents can overload transformers. They can melt the insulation. They can destroy the transformer. A single destroyed transformer can take down a large part of the grid. Thousands of destroyed transformers could take down the entire grid. Protecting the grid requires a multi-layered approach. We must reduce the vulnerability of our transformers. We must monitor the grid for GICs. We must have a plan for rapid recovery. We must invest in resilience. The first layer of protection is transformer hardening. This involves installing devices that can block GICs. There are several technologies that can do this. There are capacitors that can absorb the current. There are resistors that can dissipate the current. There are circuit breakers that can disconnect the transformer. These technologies are effective, but they are expensive. They are not widely deployed. The second layer of protection is monitoring. We must monitor the grid for GICs. We must know when they are occurring. We must know how strong they are. We must know where they are occurring. This requires sensors that can measure the current. This requires a communication system that can transmit the data. This requires a control system that can respond to the data. We have monitoring systems in place. We have sensors that measure GICs. We have communication systems that transmit the data. We have control systems that can respond. But these systems are not universal. They are not everywhere. They are not always reliable. The third layer of protection is emergency response. We must have a plan for rapid recovery. We must have spare transformers. We must have mobile substations. We must have crews that can repair the damage. We must have a logistics system that can move the equipment. We must have a plan for bringing the grid back online. We have emergency plans in place. We have spare transformers. We have mobile substations. We have trained crews. But the plans are not comprehensive. The spare transformers are limited. The mobile substations are few. The crews are small. We are not fully prepared. The fourth layer of protection is investment. We must invest in resilience. We must upgrade our grid. We must install new technologies. We must train our workforce. We must build a more robust infrastructure. This requires money. This requires political will. This requires public support. We are investing in resilience. We are upgrading our grid. We are installing new technologies. We are training our workforce. But the investment is not enough. The upgrades are not fast enough. The technologies are not widespread enough. We are not moving quickly enough. There is also the issue of international cooperation. A solar storm does not respect borders. It affects the entire planet. We need international cooperation to protect the global grid. We need to share data. We need to coordinate emergency response. We need to share resources. We have international cooperation. We have the International Space Weather Initiative. We have the World Meteorological Organization. We have regional space weather centers. We share data. We coordinate response. But the cooperation is not comprehensive. The coordination is not seamless. The sharing is not complete. The truth is that we are not fully prepared for a major solar storm. We have made progress. We have taken steps, but we are not there yet. We are not fully protected. We are not fully resilient. We are not fully ready, and time is running out. The sun is waking up. Solar maximum is approaching, and when it comes, we need to be ready. The human story. Behind the science and the technology, there is a human story. A story of dedication, a story of courage, a story of hope. The story of the men and women who are studying the sun. The story of the men and women who are building the technologies that will protect us. The story of the men and women who are preparing for the storm. These are scientists. They spend their lives studying the sun. They work in laboratories and universities. They analyze data from satellites. They build models of the sun's behavior. They publish papers. They attend conferences. They share their knowledge. They are advancing our understanding of the sun. These are engineers. They build the spacecraft. They build the satellites. They build the instruments. They work in clean rooms and control rooms. They design heat shields that can withstand 1,000 degrees. They design sensors that can measure magnetic fields. They design communication systems that can transmit data from millions of kilometers away. They are pushing the boundaries of engineering. These are operators. They operate the satellites. They operate the ground stations. They work in control centers, monitoring screens and watching for alerts. They are the ones who detect solar flares. They are the ones who track CMEs. They are the ones who issue warnings. They are the front line of our defense. These are policymakers. They make the decisions. They allocate the resources. They set the priorities. They work in government agencies and international organizations. They balance competing demands. They make tough choices. They are responsible for protecting our civilization. And there are the rest of us, the public, the people who depend on electricity, the people who depend on the internet, the people who depend on GPS, the people who are vulnerable to the fury of the sun. We have a role to play. We must support the scientists. We must support the engineers. We must support the policymakers. We must be informed. We must be prepared. There is also a personal story, a story of individuals who have dedicated their lives to studying the sun. A story of individuals who have made remarkable discoveries. A story of individuals who have overcome incredible challenges. For alerts. They are the ones who detect solar flares. They are the ones who track CMEs. They are the ones who issue warnings. They are the front line of our defense. These are policymakers. They make the decisions. They allocate the resources. They set the priorities. They work in government agencies and international organizations. They balance competing demands. They make tough choices. They are responsible for protecting our civilization. And there are the rest of us, the public, the people who depend on electricity, the people who depend on the internet, the people who depend on GPS, the people who are vulnerable to the fury of the sun. We have a role to play. We must support the scientists. We must support the engineers. We must support the policymakers. We must be informed. We must be prepared. There is also a personal story, a story of individuals who have dedicated their lives to studying the sun. A story of individuals who have made remarkable discoveries. A story of individuals who have overcome incredible challenges. We are all capable of protecting ourselves. We are all capable of surviving. The future of solar science is bright. We are launching new missions. We are developing new technologies. We are building new models. We are making new discoveries. We are moving forward. Away. It will continue to burn for another 5 billion years. It will continue to produce flares. It will continue to produce CMEs. It will continue to be the volatile, unpredictable star that it has always been. We must learn to live with it. We must also remember that the sun is not just a threat. It is also an opportunity. The sun is the ultimate source of energy. It is the source of solar power. It is the source of fusion power. It is the source of renewable energy. We can harness the sun's energy. We can use it to power our civilization. We can use it to build a sustainable future. The sun is also a source of inspiration. It is a reminder of our place in the universe. It is a reminder of our fragility. It is a reminder of our potential. It is a reminder that we are part of something larger. We live on a planet that orbits a star. That star is a nuclear furnace. It is a cosmic engine. It is a source of life and death. It is a source of wonder and fear. It is a source of inspiration and challenge. It is the sun. We are learning to understand the sun. We are learning to predict its behavior. We are learning to protect ourselves. We are learning to live with our star. We are touching the fire, and we are not stopping. We will continue to explore. We will continue to innovate. We will continue to push the boundaries. We will continue to reach for the stars. The fury of the sun is the greatest challenge we have ever faced. But it is also the greatest opportunity. It is an opportunity to understand our universe. It is an opportunity to protect our civilization. It is an opportunity to build a better future. We are not helpless. We are not doomed. We are not victims. We are explorers. We are innovators. We are survivors. We are humans. And we will not be defeated by the fury of the sun. Conclusion. We have come to the end of our journey. We have explored the heart of our star. We have witnessed its nuclear fury. We have seen its terrible weapons. We have understood the vulnerability of our modern world. We have explored the quest to understand the sun. We have seen the brave missions that are touching the fire. We have learned about the science of prediction. We have looked at the technologies that could protect us. We have heard the human stories behind the science. We have learned that the sun is not just our friend, it is also our enemy. It is a volatile, unpredictable star. It is a source of life and death. It is a source of wonder and fear. It is a source of inspiration and challenge. We have learned that we are not helpless. We are not doomed. We are not victims. We are explorers. We are innovators. We are survivors. We are humans. We have learned that we must prepare. We must invest. We must cooperate. We must be informed. We must be proactive. We must not be complacent. We must not be passive. We must not be afraid. The fury of the sun is coming. It is only a matter of time. The next great solar storm will occur. It could occur tomorrow. It could occur next year. It could occur in a decade. But it will occur. And when it occurs, we must be ready. We have the knowledge. We have the technology. We have the resources. We have the will. We can protect ourselves. We can survive. We can thrive. The sun is the star that gives life. It is also the star that can take it away. It is the fury of the sun. And it is our challenge. It is our opportunity. It is our destiny. We are the children of the sun. We are the products of its energy. We are the beneficiaries of its warmth. We are the witnesses of its fury. We are the survivors of its storms. We are human, and we will endure. The final countdown, preparing for the inevitable, the eye of the storm. We have journeyed deep into the heart of our star. We have witnessed its nuclear fury. We have seen its terrible weapons. We have explored the brave missions that are touching the fire. We have learned about the science of prediction. We have understood the vulnerability of our modern world. But knowledge is not enough. Prediction is not enough. Understanding is not enough. We must act. We must prepare. We must build. We must protect. We must face the inevitable. Part 3 of this series is about preparation. It is about the final countdown. It is about what we must do before the next great solar storm arrives. It is about the choices we make today that will determine our survival tomorrow. The sun is waking up. Solar maximum is approaching. The next great solar storm is not a matter of if. It is a matter of when. And when it comes, it will test everything we have built. It will test our infrastructure. It will test our institutions. It will test our resolve. It will test our humanity. We have a choice. We can continue to ignore the threat. We can hope that the storm will miss us. We can hope that our infrastructure will survive. We can hope that we will be lucky. Or we can prepare. We can invest in resilience. We can harden our systems. We can develop our plans. We can train our people. We can be ready. The choice is ours, but time is running out. The sun does not wait. It does not negotiate. It does not care about our preparations. It is a star, a vast, powerful, unpredictable star, and it is awakening. In part 3, we will look at the practical steps we must take. We will look at the policies we must implement. We will look at the technologies we must deploy. We will look at the plans we must develop. We will look at the training we must provide. We will look at the public awareness we must create. We will also look at the worst-case scenario. We will imagine what happens if we do not prepare. We will imagine what happens if the storm catches us off guard. We will imagine the darkness that could follow. We will imagine the chaos that could ensue. We will imagine the suffering that could occur. But we will also look at the best-case scenario. We will imagine what happens if we do prepare. We will imagine what happens if we are ready. We will imagine how we can survive. We will imagine how we can recover. We will imagine how we can thrive. This is the final chapter of our story. This is the moment of truth. This is the time for action. This is the time for resolve. This is the time for hope. The fury of the sun is coming, but we are not helpless. We are not doomed. We are not victims. We are survivors. We are humans, and we will endure. So join us. Join us as we face the final countdown. Join us as we prepare for the inevitable. Join us as we learn to live with our star. The warning systems. Before we can respond to a solar storm, we must first know that it is coming. We must have warning systems that can detect the storm and alert us in time. We must have a network of sensors that can see the sun. We must have a communication system that can spread the word. We must have a decision-making process that can act on the information. The warning systems we have today are good, but they are not good enough. They give us only a few hours of warning. They are not always accurate. They are not always reliable. They are not always comprehensive. We need better warning systems. We need systems that give us more time. We need systems that are more accurate. We need systems that are more reliable. The first step is to improve our space-based sensors. We need more satellites watching the sun. We need satellites that can see the sun from multiple angles. We need satellites that can measure the sun's magnetic field. We need satellites that can detect solar flares and CMEs in real time. We are launching new satellites. The next generation of solar observatories will be more powerful. They will have better instruments. They will have better communication systems. They will give us better data. They will give us more warning. The second step is to improve our ground-based sensors. We need more observatories on Earth. We need observatories that can see the sun in multiple wavelengths. We need observatories that can measure the sun's magnetic field. We need observatories that can detect solar flares and CMEs. We have ground-based observatories around the world. They are essential for monitoring the sun. They complement the space-based sensors. They provide data that the satellites cannot provide. They are part of our early warning system. The third step is to improve our data processing. We have a lot of data from our satellites and observatories, but we need to process that data quickly. We need to analyze it. We need to understand it. We need to act on it. We are using artificial intelligence and machine learning to process the data. These technologies can analyze data faster than humans. They can detect patterns that humans cannot see. They can make predictions that humans cannot make. They are improving our warning systems. The fourth step is to improve our communication systems. We need to be able to spread the warning quickly. We need to reach decision makers. We need to reach the public. We need to reach the operators of critical infrastructure. We have communication systems in place. We have the Space Weather Prediction Center at NOAA. We have the International Space Weather Initiative. We have regional space weather centers around the world. We have a network that can spread the warning, but the communication systems are not perfect. There are gaps. There are delays. There are misunderstandings. We need to improve our communication. We need to make it faster. We need to make it clearer. We need to make it more reliable. The fifth step is to improve our decision-making processes. We need to know who is responsible for making decisions. We need to know what decisions need to be made. We need to know when decisions need to be made. We need to have a clear chain of command. We have decision-making processes in place. Governments have emergency response plans. Utilities have protocols for grid protection. Airlines have procedures for grounding aircraft. The military has protocols for protecting assets. But the processes are not always clear. They are not always coordinated. They are not always effective. We need better warning systems. We need systems that give us more time. We need systems that are more accurate. We need systems that are more reliable. We need systems that are more comprehensive. We are making progress, but we are not there yet. We are not fully prepared. We are not fully ready. We are not fully protected, and time is running out. Protecting critical infrastructure. Once we have a warning, we must act. We must protect our critical infrastructure. We must shut down vulnerable systems. We must protect our transformers. We must safeguard our satellites. We must secure our communication networks. We must prepare our hospitals. We must protect our water supplies. The most critical infrastructure is the power grid. Without electricity, modern civilization cannot function. The power grid is the foundation upon which everything else is built. It must be protected. Protecting the power grid requires a multi-layered approach. We must reduce the vulnerability of our transformers. We must install devices that can block geomagnetically induced currents. We must have a plan for rapid recovery. We must have spare transformers. We must have mobile substations. We are taking steps to protect the grid. We are installing capacitors and resistors. We are installing circuit breakers. We are hardening our transformers. We are developing new technologies. But we are not doing enough. We are not moving fast enough. We are not investing enough. The second most critical infrastructure is the internet. Without the internet, our economy would collapse. Our communication systems would fail. Our banking systems would freeze. Our supply chains would break. Protecting the internet is difficult. The internet is a network of networks. It is a complex system. It is distributed across the globe. It is not controlled by a single entity. Protecting the internet requires international cooperation. We can protect the undersea cables. We can protect the repeaters and amplifiers. We can build redundancy into the system. We can develop alternative communication systems. But we are not doing enough. We are not investing enough. We are not preparing enough. The third most critical infrastructure is satellites. Without satellites, we would lose GPS. We would lose weather forecasting. We would lose communication. We would lose surveillance. We would lose many essential services. Protecting satellites is difficult. Satellites are in space. They cannot be hardened in the same way that ground-based infrastructure can be hardened. They are vulnerable to the expansion of the atmosphere. They are vulnerable to radiation. They are vulnerable to the magnetic field of a CME. We can protect satellites by putting them into higher orbits. We can protect satellites by shielding them. We can protect satellites by building redundancy. We can protect satellites by having backup systems. But we are not doing enough. We are not investing enough. We are not preparing enough. The fourth most critical infrastructure is water supply. Without water, we cannot survive. Our water supply depends on electricity. Pumps need electricity. Treatment plants need electricity. Distribution systems need electricity. If the power grid fails, the water supply fails. We can protect the water supply by installing backup generators. We can protect the water supply by having emergency reserves. We can protect the water supply by developing alternative sources. But we are not doing enough. We are not investing enough. We are not preparing enough. The fifth most critical infrastructure is healthcare. Without healthcare, we cannot treat the sick and injured. Our hospitals depend on electricity. Ventilators need electricity. Operating rooms need electricity. Life support systems need electricity. Refrigerators need electricity for medicines and vaccines. We can protect healthcare by installing backup generators. We can protect healthcare by having emergency reserves. We can protect healthcare by training staff. We can protect healthcare by developing alternative systems. But we are not doing enough. We are not investing enough. We are not preparing enough. The sixth most critical infrastructure is transportation. Without transportation, we cannot move food, medicine, and other essential supplies. Our transportation systems depend on electricity. Traffic lights need electricity. Railways need electricity. Airports need electricity. Ports need electricity. We can protect transportation by developing alternative systems. We can protect transportation by having emergency reserves. We can protect transportation by training staff. But we are not doing enough. We are not investing enough. We are not preparing enough. Protecting critical infrastructure is expensive. It requires investment. It requires political will. It requires public support. We are not doing enough. We are not investing enough. We are not preparing enough, and time is running out. The human factor. Protecting infrastructure is important, but it is not enough. We must also protect people. We must prepare communities. We must educate the public. We must train first responders. We must develop emergency plans. We must build resilience. A solar storm is not just a technological disaster. It is also a human disaster. It will affect every person on the planet. It will cause fear. It will cause confusion. It will cause panic. It will cause suffering. We must be ready for the human impact. The first step is public education. People need to know what is coming. People need to know what to do. People need to know how to prepare. We must communicate the threat in a clear and understandable way. We must use simple language. We must use multiple channels. We must reach everyone. We have public education campaigns. The NOAA has a space weather awareness program. The International Space Weather Initiative has public outreach. Universities have public lectures. The media covers space weather. But the education is not comprehensive. The messaging is not consistent. The audience is not universal. We need better public education. We need a campaign that reaches everyone. We need a campaign that uses television, radio, social media, and the internet. We need a campaign that is ongoing, not just when a storm is coming. We need a campaign that builds awareness and resilience. The second step is community preparation. Communities need to have plans. They need to know what to do during a blackout. They need to know how to communicate. They need to know how to get food and water. They need to know how to help the vulnerable. We have community plans. Local governments have emergency management plans. Police and fire departments have protocols. Hospitals have emergency operations plans. Schools have safety plans. But the plans are not always tested. The plans are not always exercised. The plans are not always updated. We need better community preparation. We need to test our plans. We need to exercise our plans. We need to update our plans. We need to involve the community in the planning process. We need to build community resilience. The third step is training first responders. First responders will be on the front lines of a solar storm. They will be the ones who rescue people. They will be the ones who restore order. They will be the ones who save lives. They need to be trained. We have trained first responders. Firefighters, police officers, paramedics, and emergency managers are all trained. They have skills, they have equipment, they have protocols. But the training is not always specific to solar storms. The equipment is not always designed for prolonged blackouts. The protocols are not always adequate. We need better training for first responders. We need to train them for the specific challenges of a solar storm. We need to give them the equipment they need. We need to develop the protocols they will follow. We need to support them. The fourth step is supporting vulnerable populations. Some people are more vulnerable than others: the elderly, the sick, the disabled, the poor. They will need help. They will need support. They will need protection. We must identify vulnerable populations. We must develop plans to support them. We must ensure that they have access to food, water, and medicine. We must ensure that they have access to shelter. We must ensure that they are not forgotten. The human factor is often overlooked. We focus on the technology. We focus on the infrastructure. We focus on the science. But we must also focus on the people. The people are the most important part of the equation. The people are the ones who will suffer. The people are the ones who will survive. We must prepare the people. We must educate the people. We must train the people. We must support the people. We must build human resilience. And we must do it now. Time is running out. The worst case scenario. Let us imagine the worst case scenario. Let us imagine what happens if we do not prepare. Let us imagine what happens if the storm catches us off guard. Let us imagine the darkness that could follow. The storm begins with a solar flare. A massive X-class flare erupts from the sun. The radiation reaches Earth in 8 minutes. It disrupts radio communications. It scrambles GPS signals. It interferes with military radar. The world is confused. The world is uncertain. The world is afraid. 17 hours later, the CME arrives. It is a massive cloud of plasma and magnetic field. It slams into Earth's magnetosphere. The impact is severe. The magnetosphere is compressed. The magnetic field is distorted. The currents are induced. The power grid fails. Transformers overload. They melt. They catch fire. The lights go out. All over the world, cities go dark. Homes go dark. Everything goes dark. The internet fails. The undersea cables are damaged. The repeaters are destroyed. The networks go down. No email, no social media, no streaming, no online banking, no e-commerce. The digital economy collapses. GPS fails. The satellites are knocked out. The signals are scrambled. Aircraft cannot navigate. Ships cannot navigate. Military operations are compromised. The world is blind. The water supply fails. Pumps stop working. Treatment plants stop working. Water stops flowing. People have no water to drink, no water to wash, no water to grow food. The food supply fails. Refrigerators stop working. Food spoils. Supply chains break. Grocery stores are empty. People cannot find food. People cannot buy food. People cannot get food. The healthcare system fails. Hospitals run out of fuel. Generators stop working. Ventilators stop working. Life support systems stop working. Patients die. Medicines expire. Vaccines spoil. The healthcare system is overwhelmed. Transportation fails. Traffic lights stop working. Railways stop working. Airports close. Ports close. People cannot move. Supplies cannot move. The economy stops. Law and order break down. People panic. People are desperate. People are afraid. Looting begins. Violence erupts. The police are overwhelmed. The military is deployed. The situation is chaotic. The recovery takes years, decades, perhaps a generation. The cost is trillions of dollars. The human cost is millions of lives. The social cost is the breakdown of civilization. This is the worst-case scenario. This is what happens if we do not prepare. This is what happens if we are caught off guard. This is what happens if we ignore the threat. This scenario is not science fiction. It is not a Hollywood movie. It is a realistic possibility. It is a threat that is real. It is a threat that is imminent. It is a threat that we can prevent, but only if we act, only if we prepare, only if we invest, only if we cooperate, only if we take the threat seriously. The worst-case scenario is not inevitable. We can prevent it. We have the knowledge, we have the technology, we have the resources, we have the will. We just need to use them. We must not wait. We must not delay. We must not be complacent. We must not be passive. We must be proactive. We must be prepared. We must be resilient. The sun is waking up. The storm is coming. The worst-case scenario is possible, but it is not inevitable. We can prevent it. We can survive. We can thrive. The choice is ours. The best-case scenario. Now let us imagine the best-case scenario. Let us imagine what happens if we do prepare. Let us imagine what happens if we are ready. Let us imagine the resilience that could follow. The storm begins with a solar flare. A massive X-class flare erupts from the sun. Our satellites detect it immediately. The warning goes out. The world is alerted. The decision makers are informed. The operators are called. The plans are activated. 17 hours later, the CME arrives. But we are ready. The power grid has been shut down. The transformers have been protected. The critical systems have been disconnected. The infrastructure has been secured. The CME slams into Earth's magnetosphere. The impact is severe, but our systems are protected. The transformers do not melt. The grid does not fail. The lights stay on. The internet stays up. GPS stays functional. There is some damage. Some satellites are lost. Some transformers are damaged. Some communication systems are disrupted. But the damage is limited. It is contained. It is manageable. The water supply continues. The pumps are on backup power. The treatment plants are operating. The water keeps flowing. People have water to drink. People have water to wash. People have water to grow food. The food supply continues. The refrigerators are working. The supply chains are intact. The grocery stores are stocked. People have food. People can buy food. People can get food. The healthcare system continues. The generators are running. The ventilators are working. The life support systems are operating. Patients are treated. Medicines are available. Vaccines are safe. The healthcare system is functioning. Transportation continues. Traffic lights are working. Railways are running. Airports are open. Ports are open. People can move. Supplies can move. The economy continues. Law and order are maintained. People are informed. People are calm. People are prepared. There is no panic. There is no looting. There is no violence. The situation is under control. The recovery takes weeks, Months. Not years. Not decades. The cost is billions of dollars, not trillions. The human cost is minimal. The social cost is limited. Civilization survives. This is the best-case scenario. This is what happens if we do prepare. This is what happens if we are ready. This is what happens if we take the threat seriously. This scenario is achievable. It is realistic. It is within our reach. We have the knowledge. We have the technology. We have the resources. We have the will. We just need to use them. The best-case scenario is not guaranteed. It requires effort. It requires investment. It requires cooperation. It requires political will. It requires public support. But it is possible. It is achievable. It is within our grasp. We must not wait. We must not delay. We must not be complacent. We must not be passive. We must be proactive. We must be prepared. We must be resilient. It requires cooperation. It requires political will. It requires public support. But it is possible. It is achievable. It is within our grasp. We must not wait. We must not delay. We must not be complacent. We must not be passive. We must be proactive. We must be prepared. We must be resilient.